So this is what our network architecture looks like. We've got wave gliders sitting out there in the ocean. They talk to the Iridium satellite. The Iridium satellites talk to the ground stations, and actually the ground stations are our major single point of failure. There are 2 of them in the world, and if both of them are down, then we have a problem. But they're extremely robust. We've experienced almost no outages from the satellite ground stations. But then we have replicas of everything. So we have these data clusters that run in different data centers. And then connected to the data clusters are different web apps and desktop apps. And often they'll be connected to multiple nodes. And when your data rates are low, there are a bunch of tricks you can use, like doing everything a whole bunch of times just because it's cheap, just because you don't have very much to move around. Most people, I suspect everybody in this room is kind of used to network links that start at about 1 gigabit per second, and 10 gig links are pretty normal, and 1 kilobyte. And actually, we can only do 1 300 byte message every minute. It's kind of like the maximum rate we can transmit at. So 300 bytes per minute. Repeat after me. 300 bytes per minute. It just is just a mess. So I thought I'd rat hole into a couple of sort of software nerdy things, just because you might find it entertaining. One is the way that I do streaming telemetry. When I first started this, I sort of thought, well, gee, there are all these eventually consistent databases out there. I should be able to just use one. And I could have, but the problem is that they don't fit very well. They don't deal with streams. They don't deal with authentication very well. They often don't deal with the kind of weird reliability that we need. They're often not very close to real time. It's sort of like what we really wanted was something like a publish subscribe network, something like the Java message queues, except sort of tied in with the data storage and with authentication on top of it all. Because one of the things we needed to be able to do was to be able to attach authentication to every packet, so that every packet can be, you can specify for every packet exactly who's allowed to see what, when, where. And often when the packets come through, we don't actually know what the packets are. We have sort of layers of wrappers, and sometimes people build sensors and we have no idea what's in them. And it's usually not because it's scary people. It's usually because it's some Yahoo at NOAA who's just fussing away with wires, and his bytes are his bytes. And so this system, its coefficient of reality is less than 1. Its coefficient of vapor, I think, is also greater than 0 because it's not all done. But I'd like to think that its reality is greater than its vapor. None of this is rocket science. It's sort of a lightweight, very specialized version of JMS. Very simple. Tried to use just tried and true techniques, and it's really optimized around small things, and small things that are sort of unique. So if 2 packets look the same, then they are the same, because every one of these packets contains stuff that makes it unique. They contain like a timestamp and a lat long. So if I see the same thing twice, I just look at the packet. And if the packets are equal, then I can throw one away. And that makes a lot of things really easy. It's like file systems that do dedupe by using SHA-1 hashes. I get to use the packet as its own hash. And so, like I said, it's not a big data problem. But reliability is critical, as is authentication. So our data model is pretty simple. The packets that stream through the clusters are just unique bags of bytes. There's a library of things that knows how to sort of crowbar open the packets to extract different sorts of data. We've got a number of different style of formats. There's this. Well, most of the packets today are quite literally C structs that have been just written, and they're somewhat awful. And there's a new format that is a very strangely encoded version of JSON. There are a lot of binary JSON encoders out there, but they don't have to worry about 1/10 of a cent per byte. So they tend to not be as anal about compressing the packets down as I needed to be. And you might think that, well, why don't you just like zip compress the packet? Well, or BZ2 the packet or whatever. And conventional compression algorithms do not work on small data sizes. Right? If you try using zip or whatever on a small file, it will almost always just leave it alone. But when you are paying 1/10 of a cent per byte, you actually care. So you do that with encoding of the contents of the packet. And so we have nodes in the data center. They contain these packets of data, and there's a mechanism where they can publish to people who subscribe. So there's a publish interface and a subscribe interface, and the publish side authenticates the destination. The destination say, I'm interested in this. And when you've got publish and subscribe going both ways, you just connect them up and they're chatting back and forth. The publish and subscribe are, so I publish in both directions on one TCP link. I actually use the asynchronous nature of TCP. I don't do synchronous method calls. It's just a stream each way. So one side will send a message down saying I'm interested in this, and then sort of streamed coming the other way will be data and commands and whatever. So it streams both ways, and it will sort of, if one guy gets a packet, it will replicate it there and replicate it back. So it's very efficient about the TCP links. You start putting more of these together, you end up with a mesh. And there's this sort of viral video echo cancellation. If you see a viral video on the net, you typically send it to all of your friends. And if it's something you've never seen before, you then send it off to your friends again. But if you've already seen it, that's boring. You just hit delete. And that's pretty much the algorithm that I use to propagate things through. So packets come in from the network. They hit some node. Then the nodes just replicate everywhere, and eventually it becomes consistent. Typically, it's well under a second before I get complete consistency, and so because I just replicate everything, because it's $1 a kilobyte. There's not much data, so replication works great. It means that every one of these nodes is equivalent, and if you're a client, you can subscribe to the data feed from any node anywhere. And one of the things that I do, because I'm like really paranoid, is that I don't just span data centers, I span ISPs. So I very carefully don't use any of the special ISP APIs, which is often kind of painful. But it actually works pretty well. So I currently have data cluster nodes in three different ISPs. I use JElastic, I use Entic, and I use GoGrid. I'm a big fan of Entic, even though they're like a small little outfit, but they do really nice stuff. And one of the reasons for using different ISPs is if some ISP has a bug in their software, you can cause you can get these systemic collapses, like what happens every now and then with Amazon. That you will get these weird, configuration file changed, and it'll take out, the whole East Coast. And if you've got things at different ISPs, you're unlikely to get hit by that. Also, if there are, denial of service attacks, there's always a way around if you're in a bunch of different data centers. And so if you're an application and you're getting data from this data cluster, you can subscribe to any of the nodes, or you can subscribe to several of the nodes. And one of the nice things about paranoid apps subscribing to several nodes is that so the app does the same echo cancellation trick, right? It just remembers the last hour or two worth of data. If it sees a packet that it's already seen before, it just throws it on the floor, and life carries on. And so that if a node goes down in the data cluster, the application, it's not like the application even has to fail over, right? It's still getting it from a live node in the cluster. So it doesn't even really experience the failure at the app level. The low level piece, it will, when it notices the link to one of the cluster nodes go down, it will then restart it either on that cluster node. It goes through this thing of, trying that node and trying other nodes, and the app side of it will try to make sure that there's more than one link. So besides being paranoid and giving you a lot better reliability, it also gives you an interesting performance boost, because the packet that you report to the app is the first packet that arrives. So whatever the fastest path is. So because there's not much data, I can afford to just like spew things in all possible directions, and whatever is the fastest path, that's where it goes. So real simple, really unrealistic for most people, and for this application, it works pretty well. So one of these clusters you can think of as a node, and then we do cluster-to-cluster link, so that like a customer who's like a big oil company or something, they can run their own cluster, and we'll just like spiel stuff off to different clusters. And we can do this to deliver data to customer private data centers. One of the weird problems that we have is I've had a few too many discussions with our tax attorneys. So, if we're out in the middle of the Atlantic and we collect a piece of data and we sell it to somebody in Venezuela, who do we owe tax to? And so the tax attorneys actually care about where the data resides. It can pass through places, and it seems to be pretty well established that if the data is just in motion through some jurisdiction, there's no taxes required. But if it resides someplace, so the way that this cluster is set up, you can slice and dice the data, and you can if data is never sold to somebody in the United States, it never actually resides in the United States. So it'll just go from the middle of the Atlantic to Argentina or Venezuela or wherever, and not incur U.S. taxes because there was nothing involved in the U.S. with it. And so we needed to be able to do data residency that's more complicated than just like dealing with the EU privacy laws.